Okay, good morning. Let's talk about object detection. So now we have been studying about using CNN architectures like AlexNet, VGGNet, ResNet, and so on to give a label to an image that we feed to the network. So usually what it does is converting this image through this network to some kind of a vector, and then you usually have a fully connected network giving 1,000 output because there are 1,000 classes. So for the cat class, which is the class of this image, hopefully the score should be high. This is what we have been looking at. Now, this assigns a label per class. But when you think about other vision tasks, this one is image classification. There is no spatial extent to the label that we give. It extends the full image, one label per class. Then we have the so-called semantic segmentation. Now, semantic means what we conceive as human beings as a meaning. So we can see that those semantic labels have been assigned to different parts of the image. Grass, cat area, the tree area is not here, sky area, and so on. No object, just pixels. I think I have made a mistake in coloring the tree area. This should have been in purple. Then the next one is object detection, which is very important in self-driving and so on. You need to detect cars, human beings, other signboards and so on. This is object detection. So there you can see in each image, you not only provide a class, but you also give the bounding box coordinates. This rectangle corresponds to a class called cat. This rectangle corresponds to a class called dog. So that's the object detection task. Then we have instance segmentation. There not only are the bounding boxes drawn, but the actual pixels that amount to this dog and cat have been identified. And also you can see the two dogs have been distinguished by giving two colors to the two dog pixels. First dog in red, second dog in green. I hope you understand this concept of instance segmentation also. So when you usually combine the instance segmentation with semantic segmentation, when you combine them, we call it panoptic segmentation. So this is also important for self-driving and so on, panoptic. Okay. I hope these ideas are clear to you. As usual, if you have any question, please do not hesitate to type and ask, or else you can turn on the mic and speak also. Okay, so let's look at the object detection task, which is the topic of today's lecture. Now we input a single RGB image like this one, and then the output is a set of detected objects. For each object we predict, we need the category label from fixed known set of categories, not all of them in the world, but maybe 1,000 categories, 10 categories, and so on. This is a predefined set of categories. Then for each of these detections, we want to give the bounding box also. That means four numbers, x, y, width, and height. So usually this xy is a center coordinate, and width and height, you can understand what that means. So sometimes you can give not the center coordinate, but the first coordinate also, but center coordinate is better. Okay. So here you can see there are multiple outputs. For each image, can we say that it is only one output? We cannot say that. For classification, there is only one class, one output. If there's only one object in the image, if there's only one dog or something in the image, so there is only one output. For that output, you will produce x, y, width, and height. So four number output. But now, if you have two dogs, you will have to produce eight numbers, right? But if you have a dog and a cat, you need to produce their class also, class and the bounding boxes and the size. That means five numbers per object, and therefore 10 numbers will have to be produced if you have a cat and a dog. In this image, you have a dog, and a cat. What that means is you will have to produce 15 numbers for this image. So therefore, depending on the contents of the image, the output size will have to change. Now, this is a problem for neural networks. So now multiple types of output needs to predict what category label as well as where the bounding box is. So for large images, classification works at 224 by 224. So for object detection, usually maybe perhaps you can use 800 by 600 images. So therefore you can see they are larger in size. All right. So now let's look at detecting a single object in slightly more detail. And then we look at how multiple objects get detected in slightly more detail. Okay. So, so here you can see a cat image has been input. So this can be classified also as a cat image. Now let's see, we feed it to a convolutional neural network. So usually it is pre-trained on ImageNet. So the idea of pre-training and transfer learning and so on, we did not look at it. So hopefully next week we'll be able to look at that. Next week will be the last week. Yeah. Next week, the next class will be the last week. So this produces a vector of 4096 numbers. Now, then what we do is to be able to classify, we connect it to a fully connected network, 4096 to 1000. So those 1000 nodes represent each of the 1000 classes that are in the data set. Yeah. So as we saw before, cat score should hopefully be the highest one because it is a cat image, and this answers the what question. So correct label is a cat, and we can do that with the softmax, right? So I think those things are clear. But for object detection, this is not enough. But if there is only one single object there, then we can connect another fully connected network. This fully connected network can be from this 4096 to 4 because we need to predict four numbers. Four numbers. What are those four numbers? X, Y, W, and H. And we have the four numbers of the correct box in the ground truth data set. And that for that we can use the L2 loss. Just subtract the numbers, square them, and add them so that the network will force the predicted numbers to be close to the ground truth numbers. So these are the outputs, the four outputs that shows us where this object is. So that means the something like if the ground truth block is like that, yeah, and the coordinate, center coordinate, and the width and the height relative to the image size will be predicted. Yes. I hope this diagram is clear to you. This shows the object detection problem for a single object. So how many outputs will be there by the network? What is the size of the total? What is the size of the output tensor in the what branch? Can you answer that question? What is the size of the output tensor in the what branch? In the top branch, 1000 because there are 1000 classes. And in the pair branch, in the where branch, someone has already answered. In the where branch, 4. So altogether, 1004 output, 1004 output for a single object detection for a 1000 class problem like the ImageNet large scale visual recognition challenge. I hope this is clear for you. All right. Now, you can see here the localization problem is a regression problem. What that means is we want to bring this x prime number x close to x prime, y close to y prime, w close to w prime, h close to w prime. So these are not class labels. These are numbers that we want to predict, the real numbers that we want to predict. It's a regression problem. Yeah, so then when you construct the loss, we can have a weighted sum of these two losses, the softmax loss for the classification and the L2 loss for the location. And that's the loss. And loss we minimize as we have been doing before. Any questions about this? Okay, so let's move forward. The problem that we have though is images can have more than one object. So how can we handle that? Okay, so what this means is for an image like this where there's only one cat, the output will be of this size, 4 numbers in the where branch. But if you think about this image where there is a dog, a beautiful dog, another dog, a proud cat, we need 12 numbers as the output in the where branch. Can you see that? And if you take this one, duck and the ducklings, select so many numbers you'll have to be able. Now, this is not possible for a neural network. So how do you go about doing that? Is the question in the object detection. All right. So to detect multiple objects, we can do a sliding window approach. Apply a CNN to many different crops of the image. That means locate the image, locate a window somewhere. That window you classify as a object or background. Yeah? So dog, no, cat, no, background, yes, for this one. Right? For this one, dog, yes, cat, no, background, no. For this one, dog, yes, cat, no, background, no. For this one, dog, no, cat, yes, background, no. But I'm cheating. I'm cheating. I'm locating these boxes on the objects by force, right? That's cheating. If I really want to do that, I have to move this box from box 1 pixel at a time, 1 pixel at a time. So therefore, there will be locations equal to the number of pixels in the image. And then what about the height and the width? The height and the width also you can control. So therefore, millions and millions of boxes will be there, which we will have to run through this convolutional neural network and try to get these labels. So apply CNN to many different crops of the image. CNN classifies each crop as object or background. How many possible boxes are there in an image of size h times w? Yeah, so consider a box of size small h times small w. Possible x positions, w minus w plus 1. Possible y positions, h minus h plus 1. Those are the possible positions, right? So possible positions are w minus w plus 1, h minus h plus 1. And then possible boxes, because this w and h can go from 1 to w. Yeah, 1 to w. So therefore, you have a massive number of boxes possible, this number, if you do this summation. So you can see this is not something that can be done. For an 800 by 600 image, it has 58 million boxes. No way we can evaluate them all. So then people came up with this idea, okay, let's not send all these 58 million boxes, but let's find areas that can have the potential to be an object. So these are called region proposals. Region proposals. Okay. So this one, finding a small set of boxes that are likely to cover all objects is the region proposal, often based on heuristics. Example, look for blob-like image regions relatively fast to run. Example, there is this thing called selective search. Please remember that name. It's an important algorithm called selective search. It gives 2000 region proposals in a few seconds on a CPU. Yeah. So you can think about this as the selective search output. Now you can see some candidate proposals or candidate boxes, which you will classify as object and background versus we should classify as cat, dog, background, cat, dog, background, cat, dog, background, and so yeah. Okay. So this one is this great contribution by Ross Gershik, um, and Professor Jitendra Malik has been the supervisor. Mm, is the Berkeley computer vision professor. So now you have an image, input image. Okay, we'll understand the so-called this great contribution, 2015 contribution of RCNN, how that works. So yeah, okay. Now there's this input image is there, and now you this assume that these are the region proposals. There are about 2,000 of them of these region proposals. Then what you do is on each of them, we warp the image into 224 by 224, something that the CNN feature extractor can accommodate because they can take only fixed size ones. And then you line up this so-called convolutional neural network, a convent on top of that. So for each of the region proposals, you run them through the convolutional neural network and it will produce some kind of a vector. And on that vector, you run a support vector machine classifier to classify into the different classes, and also you run a bounding box regressor on them. So bounding box regression predicts a transform to correct the ROI, the four numbers to the ground truth, because these region proposal boxes that you propose maybe have to be adjusted slightly. So this adjustment will happen in that regression operation. Okay. I hope that this is clear to you. Any questions on this? What is the problem with this? If you have 2,000 region proposals, 2,000 region proposals. For each of the region proposals, you have to run a convolutional neural network. Can you see that? So for each image, you don't only run you don't, not just running an image to a convolutional neural network, but you have to run that 2,000 times. So that you can see is computationally very expensive. But at this time, this was a great contribution because people did not know how to detect objects. So region proposals. So you can see for the region proposals, we have, for example, px, py, ph, and pw, the location, xy location, and the height and the width. Then the transformation, there's some kind of a transformation. Output box bx, by, h, bw. So bx is p, x plus p, w, tx, by, p, like that, these kind of transforms. So they have log space, scale, transform, and this kind of all these manipulations to be able to properly regress these bounding boxes. Yeah. So the algorithm was like this: run region proposals method to compute 2,000 region proposals, resize each region to 224 by 224, and run independently through CNN to predict the class scores and bounding box transform. Use the scores to select the subset of region proposals to output many choices here, threshold on the background or per category, or take top tier proposals per image, and many choices are there. Compare with the ground truth boxes. Yeah. Okay. Um, um, One thing is, if you take a data set for classification, you will have the image class, image class, image class. That means those cat images will be in one folder, dog images will be another folder, tree images will be another folder, ship images in another folder, like that. In different folders, you can put them. That's a image classification data set. What will uh, an object detection data set look like? For each image, you will have to have multiple, these 5 number and class labels, right? For each of the objects that are there in the image, you should have the 4 numbers and the class, xy, width and height, and the class, xy, width and height, and the class. So that kind of data set is required, an object detection data set is required. So you can see that's why what you mean by compare with the ground truth boxes. So in regard to YOLO, when we study YOLO, we will have a um, more understanding about this ground truth. Question: how does it support variable size boxes? So you can see it supports variable size boxes. That's a very good question. By doing this very uh, perhaps bad step by resizing them to 224 by 220 using some non deep learning method to resize them. That's a good question. Thank you. If you have any other question, you can ask. Otherwise, we can move forward. Okay, let's move forward. All right. Now, let's try to understand how we compare these boxes. And we compare these boxes using intersection over union. So you will see the value of this solely. How can we compare our prediction to ground truth boxes? So intersection or union or Jacka similarity or Jacka index can be used. Here you can see our prediction, light blue one, and the green one, ground truth. That's a ground truth box that is given in the data set. So you can see in the data set you have the center and the width and the height. So prediction will also predict those numbers. And then you can see the intersection of a union here is like about 50%, 50% overlap. Uh, so area of intersection divided by area of the union. So if IO is greater than 0.5, it's decent. So what is the maximum value that can be? IOU maximum value. Can you think about it? IOU maximum value is when the prediction box fully overlaps with the ground truth box. Then the IOU value will be 1. Area of intersection will be equal to the area of the union. When the two boxes, the prediction box and the ground truth box, fully overlap, like so. Yeah. So you understand what IOU means. So if IO is 0.7, it's very good. IO of 0.9 and so on is perfect. All right. Now the problem is when you do these detections, there will be overlapping boxes. What do you do with that? So let me correct this slight mismatch of. Some enter key has been pressed. Okay. All right. Problem. Object detectors often output many overlapping detections. Many overlapping detections. So for example, for this, the dog on the left, you can see with the P dog, probability of the dog being 0.9, one box, probability of the dog being 0.8, another box, slightly apart. But this dog also the same, a 0.7 box and probability of dog being 0.75 box. They are very close to each other. So solution, we have to do the post-process, the row detections using something called NMS, non-maximal suppression. Non-maximal suppression has to be applied after doing this detection. So what is this? Select the next highest scoring box. Select the next highest scoring box. Eliminate the lower scoring box. With IOU threshold, example greater than 0.7. Some enter key. Okay. If any boxes remain, go to 1. All right. So let's see how this works. Now take these two boxes. The sizing problems. Okay, take these two boxes. IOU between the green and the blue is 0.78. So what you do is select the next highest scoring box eliminate the lower scoring box with IOU greater than 0.7. So is the IOU greater than 0.7? Yes, eliminate that. Then take the next highest one. Next highest one is 0.75. Is the IOU between the green one and the orange one, the intersection of union? Is it, what is that? Like a slight overlapping, right? Just a minor overlap between the orange one and the green one. Green one is the one that we are considering right now. Only this much of overlap, right? This is the overlap. So you can see with that, it's 0.05. We don't over green and the blue, overlap is this much, right? That's also a small percentage. We do not take that off. So you can see for that, we only discard this and keep the green one, which is the correct one. All right. I hope you understand the NMS algorithm in this case. Then if you take the remaining ones, so 0.751 is there, 0.75 and 0.74, the 0.75 and uh, this orange one, this one, and the light blue one, we compare. And when we compare, we get 0.74. So eliminate the smaller one. That means 0.741 we eliminate. And then you can see now we have through the NMS, we have the boxes that actually correspond to the dogs. I think these are adorable puppies, golden retrievers. Yeah. Okay. All right. But now you can see this non-maximal suppression thing will have a serious problem if many that may eliminate good boxes when the objects are highly overlapping. When the objects are overlapping, this is non-NMS is a problem in a situation like this. Okay. Okay. Now we should understand, maybe I will not be able to fully explain this, understand how we can evaluate object detectors. So when two objects, when the prediction is matching with the ground truth, we know that we can use the IOU. But how do you estimate the object detectors? Because there are multiple objects in each image and the multiple ground truths in that image, multiple ground truths and multiple detections are there. So how do you find a measure that captures the goodness of that object detector? This is the question we are asking now. Okay. So you can see here all the dog detection sorted by score in that image, all ground truth dog boxes, all ground truth dog boxes. Okay. So what we do is run object detectors on all test images with NMS. For each category, compute average precision, area under precision versus recall curve. For each detection, so we'll explain that. For each detection, highest score to lowest score. Otherwise, mark it as negative. Plot a point on PR curve. Okay. Um, so let's take this match intersection of union is greater than 0.5. Let me see if there's a mistake in the animation. we can look at this to think about the precision and recall. Um, so you can see here, precision is relevant retrieved instances, all retrieved instances. That's precision. Precision means out of the things that we detected as correct, what are the correct ones? What is recall? Now, all the correct ones, how many have been able to retrieve? Okay, let's look at this diagram and we can understand. So you have the relevant elements. These are the relevant elements. These are the elements that we have been able to retrieve. When we have retrieved, we retrieve the good ones as well as bad ones. So these are the true positives. So relevant from the relevant elements, what we have been able to retrieve are called the true positives. And these we could not retrieve. And we call them negatives, but they are not actually negatives. So we call them false negatives. And then in this case, these we could not retrieve. So, but these are true negatives, and we retrieve these ones, and these are negatives, and we said, okay, these are good ones. So therefore, these are called false positives. These are negatives, and we did not retrieve them. Also, so these are true negatives. This part is okay. This part is okay. This part is bad. This part is bad. So how many relevant items are retrieved? Relevant items. So from all retrieved ones, that means a circle, what are the relevant ones? Relevant retrieved instances, all retrieved instances. I hope you understand what precision means. Then recall means from all the relevant items, these are all the relevant items, this one, how many we were able to recall. Yeah, recall. Okay, this is the precision and recall. All right. So now let's see how to come up with this average precision, this metric. So all dog detection sorted by scope. So first of all, you can see with this ground truth dog box, this matches with IOU greater than 0.5. So precision is, you can see, we have retrieved that. That's 1. But out of the all relevant ones, that means all dogs, only one has been detected. So recall is 0.33. I hope you can understand that. And then next one is this one. So now you can see at this stage, we have precision 2 out of 2, all 2 are correct. But recall is 2 out of 3. At this stage, so if there's no match greater than 0.5, this is the case. So you can go through this animation and somehow um, you can obtain these numbers and you plot a curve, precision versus recall curve. And then the area under this precision versus recall curve is a dog average precision. Dog average precision, only for the dog class. How to get average precision equals 1? Hit all ground truth boxes with IO greater than 0.5 and have no false positive detections ranked above any true positives. So this is how to get the AP equals 1. But this is only dog AP. When we have other objects also, and we have their average precisions also, we add them and get the mean, we will have the mean average precision, or MAP. MAP. So some people have uh, different MAPs. Uh, so if you take the COCO, I hope I can quickly go into that. Um, So Coco, these common objects in context, I think Microsoft did that. I think they have that like objects and so you can see here. Now in the COCO matrix, the following 12 metrics are used for characterizing the performance of an object detector on COCO. So AP, average precision IO is 50%, 0.05, and 0.95. So this is they take all these average precisions and different IOU scores. So then that's what they call as AP. And then they will have at 50% match average precision. So this is actually the Pascal VOC metric of a previous data set, and they will have IOU 0.75 also. So you can see when you say AP and when they write a number, AP 50%, what that means, 50% overlap. So unless otherwise specified AP and okay, whatever that means, I don't know what that means. AP is the average of all categories. Traditionally, this is called mean average precision. We make no distinction between AP and mean average precisions, and so this they call both of them average precision. Yeah, but usually people call it MAP, mean average precision. Okay, so I hope you understand the metric that is used to do object detection. Uh, Okay, evaluating object detectors mean average precision. Run object detector on all the test images with NMS. For each category, compute average precision under area under the precision versus recall curve. For each detection, highest score to lowest score. Otherwise, mark it as negative. Plot a point at PR curve, and then you can get the average precision. Mean average precision, average AP of for each category. So for COCO, MAP and threshold, they have so many IOUs and take the average. I hope my interpretation is correct. If there's anything wrong in that interpretation, please let me know. Maybe I made a mistake there. Okay. Uh, Now let's once again look at RCNN. Uh, It's called region-based RCNN, and we looked at it before, and we understood that how it is done. It is done by getting these region proposals. In this image, there are 3 region proposals shown, but usually there are 2000. And each of the region proposals we resize to 224 by 224. As someone asked a question about that. That's a very important question. It's resized. Then run the convolutional neural network on each of them. And then we'll have finally a number like 4096. That number you used to do run to a classifier, support vector machine classifier, to give the class for this and for this one. For example, this is a human being. Maybe you get the person class. For this one, I don't know. If you have another bounding box with horse, it will say horse class. And then we will have a bounding box regression, the predicting the 4 numbers regression. So this is the uh, thing about RCNN. But the problem is uh, it is very slow. So need to do 2000 forward passes for each image through the convolutional neural network. That's why RCN is very slow. Okay. Solution. Now you can see the beauty of this solution. Run CNN before warping. Run CNN before warping. So that is the thing about the fast RCNN. So you can see on the right-hand side the structure of RCNN. You can see the structure of the fast RCNN now. You run the convolutional neural net, AlexNet or ResNet once. And then you have the convolution feature map. And then oh, you still have the region proposals from the, it is from a old paper called selective search, right? Selective search, right? Selective search. So these selective search based region proposals are there. Those region proposals you locate on the convolutional feature map. That's the confi feature map. It has been resized to the image size, and then you locate these region proposals. And for those region proposal, you extract the features. For this region proposal, you extract the underlying features. For this region proposal, you extract the underlying features. So you can see that you had in the previous one, you had to run the convolutional neural network 2000 times. In this one, you just have to run that once. So don't you think that's a great achievement? So to get the features corresponding to each of these region proposal regions, we have something called ROI pooling, region of interest pooling. That is crop and resize images. So then for each region, we have a very small network to give you the class label and the bounding box category. The advancement made by fast RCNN paper by the same authors in comparison with the RCNN paper. I hope this is clear to you. RCNN is a very accurate. Actually, we usually use faster RCNN. I'll show that next. It's a very accurate object detector. Still, not too bad. Okay, let's move forward. Um, so you can see here, most of the computation happens in the backbone network. This saves work for overlapping region proposals. Per region network is relatively lightweight. So example, when using AlexNet for detection, 5 convolution layers are used for backbone and 2 fully connected layers are used for each region, per region. So like that, for example, ResNet last stage is used as per region network. The rest of the network is used as a backbone. Okay. Yes. So let's look at briefly the method of ROI pooling. You have the CNN. Now that the region proposal box is sent to the CNN, and then project object proposals onto the feature. These object proposals are from the selective search and their size is known on the image. And then the feature map is of different size, but we project that onto the feature map. Like so, assume that this is the uh, region proposal box. So then you snap to grid cells. You find the closest ones and snap to that. Divide into 2 by 2 grid of roughly equal regions, and then region features. Here 512 2 by 2 in practice. Example 512 7 in practice it is 512 7 by 7. Region features always same size, even if the input regions have different sizes. This is what they do. Max pool within each subregion. Snap to the grid and max pool within each subregion. Snap to the grid and max pool. This is what ROI pooling means. Okay. Problem, slight misalignment due to snapping, different sizes subregions is weird. So uh, problems. Because of the snapping problem, you can see the subregions are different sizes. This subregion, if you take, it's a 2 by 2 subregion, right? This subregion, if you take, it's a 3 by 2 subregion. So different sizes. This happens because of the snapping waveform. Yeah. So there's a small illustration. You can see how ROI pooling happens, right? Region proposal, divide and pick the maximum. It's a stupid thing to do, right? You can see it's not very good, not very nice. Okay. So there's a thing called ROI align also that came in this mask RCNN paper, which won the best paper award in ICC 2017. Then you have once again the CNN, and then you have the object proposals onto the features, and we don't do no snapping. We don't do snapping. So you can see divide into equal size subregions, not unequal subregions, and then sample features regularly spaced points in each subregion. And then we bilinearly interpolate and find these values. Yeah, interpolation. So like so. So you can see the pixel values are available only at the particular locations. These locations, right? Okay, pixel values are available at the center of the pixel, right? The center of the pixel, the center of the pixel, the center of the pixel. Based on those four center values, pixel values, we should evaluate this location's probable value. So for that, we can use all these four pixels in a bilinear optimization, bilinear interpolation manner. Okay, so you can see the pixel values have been sort of indicated there. Features x5 points x5 is a linear combination of features from its four neighboring grid cells. So anyways, how do you find that? This is a differentiable. Upstream gradients for sample features will flow backward into each of the four nearest neighbor grid points. So this is also an advantage. Okay. So after sampling, max pooling in each region. After sampling, max pooling in each region. So you get the maximum value in each region. Yeah. So region features 512 by 2 times 2. So in practice, 5 divided by 7 times 7. So I hope you can understand the difference between ROI pooling and ROI align. In ROI pooling, the grid snapping is there. Regions of different shapes and they have been snapped. In ROI align, grids of the shape by sub regions of the same size, and bilinear interpolation is used to get the numbers and then do the pooling. So now you can see the difference between the slow RCNN and the fast RCNN. In the fast RCN, we apply differential cropping to shared feature computation method. Slow apply differentiable cropping on the shared image features. This is wrong. I don't know what I have written. Okay. So when you compare the time taken for these, now if you take the training time, RCNN 84 hours, and SPP net is there. I don't know what that is actually. I don't remember. The fast RCNN 8.75 hours. That's great. But when they compare the testing time, they realize this. In the RCNN, executing the region proposals took that many, and including region proposals took that many. So you can see SPP net in the fast RCNN, excluding region proposals takes this much time, including region proposals takes this much time. So in this one, although here they are okay, in this one you can see the time difference is huge, right? Because the time has become smaller. So region proposals are taking time in this fast RCNN. In the RCNN, the time taken is so huge, so you don't care about those differences. But now you care. So that means this the conventional way of doing region proposals is time taking. recall region proposers compute heuristic selective search algorithm on CPU. And the idea is now we can learn them with the CNN instant. That's the next step of this. And that gave rise to the faster RCNN, the third iteration. Um, uh, that's a great the culmination of this line of work. RCNN, fast RCNN, faster RCNN, and this is still a very good object detector. So here you can see, rather than using selective search, they said, okay, let's use the same CNN feature map. That's a feature map. And on that feature map, let's run a region proposal network. Insert a region proposal network, RPN, we call it an RPM, to predict proposals from features. Otherwise, same as fast RCNN, crop features of each proposal classified. So this is the only thing that they did, so that it became very fast. From this feature map that you have, you predict the region proposals. So these proposals send bounding box regression and the classification loss. So after that, you have these rectangles, and for those we have the features for each of them: bounding box regression and classification loss. But you can see now the bounding box regression and the classification loss are there in both the region proposal networks and the final object detection layer. So you have to come up with some mechanism of alternating back and forth between them. So which they did in the paper. Yeah. So now let's look at the cropping features in the ROI pool. Run backbone CNN to feature aligned input, features aligned to the input image. Image as an anchor box fixed at each point on feature map. And then you can see the anchor boxes and the feature maps. Anchor is an object. Is anchor an object or not? So if you have a 20 by 15 grid here, we have 20 by 15 grid here, each grid point has 512 features. We ask, is anchor an object or not? That decision. At each point, predict whether the corresponding anchor contains an object per cell. Logistic regression predicts scores with con layer. And imagine an anchor box of fixed size at each point in the feature map. These are the anchor boxes. And box transforms. Now, these anchor boxes, through the regression, we transform. So this transformation is computed. For each of them, 4 numbers to transform the location and the height and the width. So this is the anchor boxes concept. I think the title of this slide is wrong, anchor boxes concept. For positive boxes, also predict a box transform to regress from anchor boxes to the object box. So at test time, sort all k times 20 times 15 boxes at each score and take the top 300 as region proposals. Now, this is, if you take k of them, rather than just one anchor box at each cell location, k of them, you will have 4k box transforms. And you can see how this region proposal thing is successful on the CNN feature map. At test time, sort all the k boxes at their score and take top 300 as our region proposals. Okay. To summarize once again, how do you do the region proposal thing? We have the image and we have the convolutional neural network that gives the feature map of this size. At each location, you locate these anchor boxes of a certain size and a certain center. And for each of them, we predict whether there's a box or not, box or not, box or not. So for each location, you can predict k objects to be present or not. Then for each of these k, you predict the transformation. So that anchor boxes resize. So at test time, sort all k times 15 times 20 boxes by their score and take the top 300 as the region boxes. So you can see this is how the region proposal network will. Okay. All right. So there are four losses in this fast RCNN. RPN classification, anchor box is object or not an object loss. Region proposal network or regression, predict transform from anchor box to proposal box. Then object classification, classify object as proposal as background object class. Object regression, predict transform from proposal box to object box. So you can see these four losses are there because we have the region proposal network as well as a final detection layer, uh, classification loss, bounding box regression loss, classification loss, and the bounding box regression loss. So these are for this one, right? These are for this. Okay. So now you can see the test time speed from RCNN, SPPNet, I don't remember, fast RCNN seconds, and fast RCNN, fast RCNN 0.2 seconds. That's extremely fast, right? So this is an excellent achievement. Any questions? Okay, let's move forward. Fast RCNN learnable object proposals. There is the because there are the region proposal network also. There is a certain way of having to compute this. Fast RCNN is a two-stage object detector because the region proposal network and the this are there. So first stage, run once per image, backbone network, and the region proposal network. And the second stage, run once per region, crop features, pool align, predict object classes, predict box offsets. So you can see the operations run for this stage, the first stage, and the operations run for the second stage. So that's why these are called two-stage detectors, because there is the region proposal network part. Region proposals, and each proposal you classify and bounding box regress. So these are called two-stage detectors for this reason. How do we really need, do we really need the second stage? Of course, you can ask that question. Then, then people came up with the single stage detectors, run the backbone CNN to get the features aligned to input image. And then you have, so you can see, and then the features are there. For each of the key anchors, you can have a class. Remember the key anchors at each position in each image feature map. RPN classify each anchor as an object or non-object. Single stage detector classify uh, each select object as one of the C categories of the bound background. So that also you include in this prediction structure output. That's how you make this from second two stage to a single stage of bit detection. So sometimes they can use the category specific detection also. For dog class, cat class, and so on, we can use category specific box detection, predict different box transforms for each category. Okay. I will briefly summarize what we have discussed up to now. First of all, we understood that object detection is very different from image classification. In image classification, we give one label per image. In the object detection, if there's only one object in the image, we have to give four numbers, where the object is, the center, and the width and the height. But when there are more than one object in the image, undefined number of objects, then there is a problem. We can use the sliding window approach, then there will be millions of sliding windows. So it is not possible to do. So therefore, people came up with this idea. Let's use a non-deep learning based selective search region proposal system. So on each of these region proposals, they ran the convolutional neural network and the classification SVM and the bounding box regressor, that was RCNN. Then they realized that this RCNN needs the convolutional neural network backbone to be run 2000 times for each image. This is computationally expensive. So therefore, they decided to run it once and then do ROI pooling. That means for each of the region proposals, you pool the features out. That is fast RCNN. Faster RCNN, of course, uh, got rid of this selective search and introduced the region proposal network, or the RPN. Then people thought about, like, why do you have to do this RPN and the uh, classification part separately? Classification and regression part separately. Can't we do it at once by providing a larger structure, predicting a larger structure? So that one gave rise to single state detectors, where two stages are not used. Okay. So with this background, we can understand what this diagram looks like. So this diagram shows the GPU time and the overall mean average vision. So you can see there they are showing fast RCN ones in circles. Okay, RFCN, these are fully convolutional network, that one data, and SSD ones, single state detectors in diamonds. So you can see with the different backbones, VGG, ResNet, Inception, V2, and these are efficient backbones. So you can see for if you take this circle, for example, that's with this kind of a GPU power, and it is producing good overall MAP. So you can in general see that the single state detectors, the diamonds, of less accuracy because their flexibility is small. Okay. Now two-stage methods, faster are seen and get the best accuracy but are slower. Single stage methods, SSD, are much faster but don't perform as well. Bigger backbones improve performance but are slower, diminishing returns for slower methods. Those are the takeaways from this diagram. Okay, let's move forward. But then this is not the only detector, so there are other detectors. Fast RCNN with ResNet 101. If it's FP means feature pyramid network thing is there. So there you can see circle has come here. That's with the low GPU, high accuracy. Then fast RCNN with the rest next and FPN, longer training. So you can see many things like that are there. Mask RCNN, much faster, RetinaNet. Mask RCNN with rest next here. So you can see these results are few years old. Since then, GPUs have gotten faster, and there's improvement performance with many tricks. Training longer, multi-skill backbones, feature pyramid networks. These are called multi-skill. That means you use features not at the very end, but features from lower layers also. Single stage methods have improved. Very big models work better. Test time augmentation pushes numbers up, and so on. And then they had ensembles also. That means collection of things. And apparently that has won in some year. You have the if you want to use these things, there are these TensorFlow detection API. and Detectron 2 in PyTorch. I think it's quite easy to get them working fast mask RCN and RetinaNet. All these things are there. So you can see one more thing is object detection progress. This is up to hmm, before CNNs, before AlexNet came, they have been sort of 40% average precision. Then after mean average precision, after that, after CNNs have been introduced, they have grown large. You can see, right? Okay. So in summary, we looked at slow version of the RCNN network. So you can see the region proposals, each region proposal resized, a coordinate running on region proposals, and the support vector machine classifier, and the bounding box regressor. And then we looked at the fast RCNN, where only one convolutional backbone is run on the image, and then region proposals are mapped onto the final feature map, and those feature maps are pooled and resized, and then a very light network is run on top of them to give the class and the bounding box. Then in the faster RCNN, we have the region proposal network. And because of that, the training has to happen in a certain manner. In the single stage fully convolutional detector, we don't need this branch, and we do the bounding box regression and classification loss. And with these proposals, and we are able to detect objects, but you know that single stage detectors are less accurate, although fast, compared to two stage detectors. Okay. So I think it's a good time to take a break. So we will meet at 12:10 after the break. We'll meet at 12:10. Hello, welcome back. So let's look at single stage multi-resolution detectors. Mainly, we want to look at the YOLO and how to get YOLO run, and how YOLO works briefly, and what kind of data sets that YOLO accommodates. Mm. Yes. Okay. So just before the break, we looked at the faster RCNN pipeline. It has the convolutional feature map that is generated. And on top of that feature map, we run the region proposal network, and we have the RPNs. And then these con features are there. And based on the RPM boxes that we get, these kind of boxes that we get, we have the ROI pooling done. And then we have the ROI features for each of these regions, and then we do detections, classification, and regression on that. Then the question is it possible to detect in one shot? So convolutional feature map of the entire image is there, the same map, and can we do classification and regression directly on that map and get the detections. So this is the idea of these single shot detectors. Um, we will see how the YOLO works. Mhm. So in YOLO, we divide the image into coarse grid. So we will look at that in detail, S by S grid on the image, and directly predict the class label and a few candidate boxes for each grid cell. So um, we will first open the YOLO paper and browse through it briefly, and then go into details of how these different colors have been obtained. What is this class probability map, and what is this bounding box and confidence for each of these boxes that are located. Um, Many of these boxes that are located at each of these cells, and then how the final detections are obtained. That's the YOLO paper. So many, as you know, many YOLO versions are available. Uh, the original one, I don't know whether they still have the website. This is the website of the Joseph Redman. He's the one who is the first author of the YOLO paper. And then he came up with this YOLO couple of versions only. And then after that, other companies took over, I think, using the same name. Um, so one thing is the meaning of YOLO. It's you only look once. You just have to look at the image once, not two stages. That's what that means. So about the paper, we interrogate the paper. It's a paper. Is the YOLO original paper, highly cited. So you can see in this one is an object detector. You can see detector. You can see the multiple boxes drawn, and they show the probabilities also with the boxes. So this is the diagram that was there. Uh, Then we'll briefly read this paper, this important parts here, unified detection part. You unify the separate components of the object detection into a single neural network. Our network uses features from the entire image to predict each bounding box. Oh, it also predicts all bounding boxes across all classes to an image simultaneously. This means our network reasons globally about the full image and all the objects in the image. The YOLO design enables end-to-end training and real-time speeds while maintaining high average prediction. Our system divides an image into S times X grid. So this is that S times X is grid. Usually it is 7 by 7. If the center of an object falls into the grid cell, that grid cell is responsible for the detecting that object. So please remember that. So I will show images of that in the slides. Each grid cell predicts B bounding boxes. How many bounding boxes? Usually two. And confidence scores for each of these boxes. These confidence scores reflect how confident the model is that the box contains an object and also how accurate it thinks uh, that it predicts things that it predicts. Formally, we define confidence as probability of object times IOU with the truth, the ground truth. So you can see the object prediction can overlap with the ground truth up to a certain extent, right? So we measure that using the IOU. If no object exists in that cell, the confidence score should be 0. Otherwise, we want the confidence score to equal to the intersection or union between the prediction box and the ground truth. Each bounding box consists of 5 predictions, X, Y, H, and the confidence. H, Y, X, and the confidence. The X, Y coordinates represent the center of the box relative to the ground truth grid cell. The width and the height are predicted relative to the whole image. And this also please note. So there are these little boxes that are there. And uh, with respect to those little boxes, the center of each object, XY coordinates are taken with respect to the location, the corner of each of these boxes. So they are related to the corners of these boxes. But when you take the width and height of the image, they are taken relative to the image. So what is the percentage from the image? So please remember that also. Finally, the confidence prediction represents the IOU between the prediction box and any ground truth box. Each grid cell also predicts C conditional class probabilities, probability of class I, dog, cat, or whatever, given that there is an object, given the object. These probabilities are conditioned on the grid cell containing an object. That's what this notation means. We only predict of where is we only predict only one set of class probabilities per grid cell, regardless of the number of bounding boxes. So that's fine. You can see for each of the cells, there is one color. Each color, this pink represents the car. Pink color represents the car class. You can see that, right? The orange represents the bike class. The green represents whatever class, I don't know. Red also, I don't know, but the blue represents the dog class. So you can see it has 1, 2, 3, 4, 5, 6, 7, 7 by 7, 49 cells. Each of the cells will have a class with the highest probability. Yes. Uh, Regardless of the number of boxes, that means at each cell they look at two boxes, we said, but independent of that, regardless of that, they predict only one class per cell. At the test time, we multiply the conditional class probabilities and the individual box confidence predictions. So the class probability given an object and the probability of an object and IOU with the ground truth. Okay, so you can see this, which gives us a class-specific confidence scores for each box. These scores encode both probability of the class appearing in the box and how well the predicted box fits the object. Okay, so let's look at this one example here. Our system models detection as a regression problem. It divides the image into S by S grids. For each grid cell predicts B bounding boxes, confidence for those boxes, and C class probabilities. These predictions are encoded as an S. Now, this is the key thing that we need to understand. S times S times B times 5 plus C tensor. So S times S, I think you can understand what that means because each of the grid cells. Each of the grid cells, what do they predict for each of the grid cells? They predict, okay, number of bounding boxes. There are, let's say, two bounding boxes for objects of this shape and objects of that shape, let's say. Two bounding boxes. Now, for each of them, they predict five numbers. What are those five numbers? Those five numbers they said here. Those five numbers are uh, the center XY, the width and height, and the confidence. Confidence. Okay. So five numbers. And C, what is the C? The class probability. Class probability. So in this cell, what is the bicycle probability? What is the car probability? What is the dog probability? And so on. And but that cell will have the highest probability. That is a class of the objects that are centered in that cell. Okay. One example, for evaluating YOLO on Paxel VOC, we use S equals 7, 7 by 7, B equals 2, 2 bounding boxes. Pascal uses 20 label classes. So C is equal to 20. So then the final prediction tensor is 7 times 7 times 30. I hope that this is clear to you. Okay. There's a quiz question also on this. So that's why I explained using the paper itself. All right. Now, let's go back to the slides. So I hope now you understand this diagram. Any questions about this diagram? Okay, let's move forward. Okay, so now we can briefly look at this YOLO architecture. So they take the convolutional feature map at 7 by 7 resolution. So you can see when you look at the output structure, Here it is a 7 by 7, 7 by 7. So now you understand why it is 30 also. Because as I mentioned, there are in the Pascal VOC, there are 30 classes. Sorry, there are 20 classes and two bounding boxes B. And this is for each bounding box, you have to predict X, Y, W, H in the confidence. That's why there are 5 numbers there. So altogether, this is the size of that structure. So you can see why this is like that. So again, that 4096 thing is there. So even in the previous classifiers that we saw, this was the case. So they have usually they take 448 by 448 images, initially a 7 by 7 convolution uh, uh, with the stride 2, I think. So therefore they resize it to 112 by 112. Um, because there's a max pooling layer also. So on plus max pooling, so size is divided by 4 because of this stride as well as the max pooling stride. And then they have run 192 of those filters. So I hope now you can understand these things after the convolutional lectures given last time. And then they run once again 3 by 3 convolutions. And then max pooling, because of that size becomes half, 56 by 56. And then again 3 by 3 convolutions. Uh, um, so crazy convolutions. So I did not go through this, so I am not ready to explain that. So then max pooling is also they are here. So uh, finally, the size becomes 28 by 26 because of the max pooling. This convolution one, actually, I did not go through that. Mhm. Yeah, so anyways, we can just see that. So one by one convolutions generating 128 uh, feature maps, 3 by 3 convolution generating 256 feature maps, and on top of that 1 by 1 convolution generating 256 feature maps, and finally 3 by 3 convolution generating 512 maps, resulting this one. Yeah. I don't know why. That's the structure they decide. Then again, some convolutions and then max pooling. So the size has become 14 by 14. Then finally, some more convolutions, two of them. And then once again, stride 2 convolution also. There's no max pooling there. So you have the 7 by 7 structure. There again, they run some convolutions. Then finally, you get 4096 numbers. So this is the YOLO's original YOLO's architecture. Yeah. So if you have any questions, as usual, please do not hesitate to ask. It's a very important detector, as you know. Okay, now let's look at the ground truth that must be there for YOLO. So I think this will once again reinforce what you already know. I think you already know this now. In YOLO algorithm, if you use 7 by 7 cells and there are 20 classes for each training image, what will the ground truth tensor look like? Okay, let's reason out that again. Input image is divided into an S by S grid. Here S is equal to 7. So the grid has 7 by 7 and 49 cells. I did this calculation for 5 by 5. That's why this mistake. 49 cells. Each grid cell is responsible for predicting the objects whose center falls inside the cell. For each cell, YOLO predicts, what does it predict? Bounding box coordinates x, y, wh. But we have to remember from the paper we saw that xy is related to the cell and wh is related to the image. Confidence scores probability of the box, probability the box contains an object times IOU with the ground truth. That we saw in the paper. Class probabilities distribution over all C classes. Here, number of classes is 20 because of that Pascal VOC dataset. In YOLO V1, each cell predicts B bounding boxes. They usually use 2. So therefore, these 5 numbers for bounding box 1 and another 5 numbers for bounding box 2 and the class probabilities for the 20 classes. So out of them, 1 will be the highest. So in this case, if 5B plus C, uh, uh, 5 times B, so that is 10 plus 20, 30 numbers per cell. So therefore, ground truth tensor should be 7 by 7 times 30. So if you have, if you get a ground truth data set, that means you are given image and you will get some coordinates in a JSON file or something with the object class 1, its bounding box, objects class and its bounding box. Like that, you have to construct this kind of ground truth tensor to be able to train YOLO. So YOLO outputs this much, this size of a tensor, and the ground truth is also this size. Then you can find the find some losses between those. So we will look at that also. Okay. So once again, to reinforce what we discussed, how YOLO works. So probability of an object being there, this number, bounding box X, bounding boxes X. So let me check. I'm sorry about that. I should have checked that. One number is missing. It's okay, right? A bounding box is X coordinate, Y coordinate, W coordinate, H coordinate, and the classes up until 20. Okay, you can have more than that classes for that data set, only 20. Okay. Now let's take this image. So this image has a cat and a dog. Now we locate a grid on that image, a 7 by 7 grid. Now you can see different grid cells. As a human being, you can understand which class maximizes for those grids, right? For example, if you take uh, this example, I'm taking only 3 classes. I'm taking the cat class, the dog class, and the tree class. Yeah. So if you take this box, this one, now this is the ground truth cat box. So in the ground truth image, we would have gotten that. Let's assume that this is the ground truth image. If this is the ground truth image, okay, it's a square image. The cat is here. This is the cat. So the ground truth image would have had this bounding box, right? The ground truth image. The center coordinate and the width and the height. Yeah. So that's the ground truth box I'm drawing here. That's the ground truth box. So center of that ground truth box falls in that particular cell, this cell. Now that cell is responsible for detecting that cat. Okay. So now for that particular cell, we have to have in the ground truth, this is 1. Probability of an object being there is 1. Within that cell, maybe this is about 0.7, 70% of that cell, right? That's 0.7. And this is about 0.8, right? This is about 0.8. See, it is in the cell, the numbers inside the cell is 0.7 inside the cell. With respect to this corner of the cell, with respect to that corner, 0.7 and 0.8 are the X and Y coordinates of that. These two numbers, X and Y coordinates. Okay. Then Now I have to give the size of the bounding box. That size of the bounding box is, this is the height of that. That height, you can say it is about 40% of the image, right? That is why it's 0.41. This width is about 30% of the image. That's why 0.3. Okay, I just put these numbers, but you can see that they sort of make sense, right? Yes. Then um, in the ground truth, this is the cat class. This is the cat class. So that cat probability is 1, others are 0. That's the ground truth vector for that cell. For each of the cells, this kind of a vector will be there. I hope that's clear to you. Okay. Now let's take another cell. Okay. So I have shown you again this way of getting the coordinates. So this one we consider as points 0, 0.0, this one 1, 1. And based on that, I got this number as 0.7 and this number as 0.8. I hope that's okay. Okay. But if you take a cell where there is no object, this one, this cell, if you take this cell, there is no object in that. So you put 0 here and all these numbers are zeros. Nothing to be there. All these numbers are zeros. No object. Okay. If you take the dog one, so there you can see probability of an object being there is 1 for that cell. We are talking about this cell where the center of the dog falls in the ground truth. And I'm measuring this distance from this corner to be about 90%. This distance from this corner to be about 30%. And 44% uh, from the image height, and about 49%, about half, from the image width, the ground box. And cat probability is 0, dog probability is 1. Okay, so I hope that is clear to you. How each of these cells will be assigned a vector of a particular size, and that size we know 2 times bounding box, number of bounding box, sorry, 5 times the number of bounding box plus the class probabilities. So here I am considering B equals 1. Number of bounding boxes equals 1. In the YOLO paper, they used 2 bounding boxes. Okay, now we can represent that structure that we will have. So each of the 7 by 7 ones will have how many numbers? 1, 2, 3, 4, 5, 6, 7, 8 numbers. 7, 8 numbers will be there. So you can see this is the depth 8. 8 numbers at each location. So now we have to design the neural network to, for each image, you output this structure. So irrespective of the number of objects in that image, you output that structure in YOLO, right? I hope this point is clear. Mm, This is clear for you. Okay, now let's look at the YOLO's objective function or the loss function. It is a very complicated one, but it is not difficult to understand. Mm. You will actually realize why that is needed. Okay, for all the bounding boxes and for all the cells. Okay, S is equal to 7, remember? And number of bounding boxes is 2 usually, right? If there is an object, this in I means indicator 1 or 0 if there's an object 1, if there's no object 0. You get the error from the ground truth x coordinate and the ground truth y coordinate. That's a location error, coordinate error. Also, the same summation, if there is an object, the width error and the height error. Width error and the height error. And if there is an object for each of the cells, the class confidence scores. This I don't remember. I'm sorry, this is not the class confidence. So, object or no object. If there's an object, ground truth will be 1, this will be some number. The network will predict some number. So you want to push that to 1 if there's an object, that one. This part is the one I don't remember, really understand. Maybe we can look at the paper and understand why they want to have, if there's no object, also some loss. That means for areas that do not have objects like background, yeah, now I think I remember, they want to force the object confidence to go to 0. For no object ones, the ground truth will be 0. They will want this also, the predicted, I think this is the predicted one, I'm sorry. Hat is a predicted one. They want the predicted one. So this will be 0 for no object. This no object ones. They want the predicted one. If the predicted one is 0.9, that's bad, right? That's making an error. So this 0.9 may somehow reach to a very small number. Something like that because of this loss. So you can see for background uh, cells, it's pushing that to 0. For foreground ones, that means for object ones, it's for object ones, the ground truth will be 1. This will be pushed to close to 0.99 or something like that. I hope that's understood. And then finally, for each of the classes, they will want the system to match the ground truth class probabilities. Ground truth class probabilities. In this, only one will be 1, as we saw in the previous slide, right? In the ground truth one, only one of them will be 1. So all others must be 0. So, but this network will not predict like that, right? It will predict some probabilities and they will be sort of try to be pushed to the ground truth probability vector. So I hope that this is quite clear to you now, how the YOLO loss function works, how the YOLO structure is constructed, how the loss function works. I hope now you sort of understand how this important classifier called YOLO works. Any questions about YOLO? No. So this is this, once again, cell I contains an object. Predictor J is responsible for it. small deviations matter. Oh, I forgot to explain that. Why did they get the square root for the sizes? So small deviations matter less for large boxes than the small boxes. So you can see if the boxes are small, this is the okay, this is the ground truth box. Okay, let's see large box. This ground truth. Okay, ground truth. This is a ground truth. And let's say I will draw the uh, this is the prediction. So I will draw get this much error for the ground truth also. This much error. So now you can see the predicted one is here. For a small box, this is very bad. For a large box, it's okay. So therefore, small deviations matter less for large boxes than for small boxes. That's why they get the square root like this. So you can see for every single decision they rightly made that confidence for object, confidence for no object, and downweigh the losses from boxes that don't contain objects. Uh, no object means 0.05, I think that I don't understand in the class probability. Okay. Any questions about the loss function, objective function? So when you want to understand a paper or some system, as you can see, so the my trick was I carefully looked at the ground truth data. So that's why I gave this slide to you. Actually, I was inspired by this video here. You can see I have listed that. I explained you what ground truth should look like. If ground truth looks like that, then you know how the objective function should compute. Then you understand the network to be able to give that good prediction. You should design the network. That's also to understand the paper. Look at the ground truth. What does the ground truth contain, and what is the loss function? And then look at the network. Okay, these are clear, I hope. All right. Then let's briefly look at each grid cell YOLO, the outcome of YOLO results. Each grid cell predicts only two boxes and can only have one class. This limits the number of nearby objects that can be predicted. That's a limitation of YOLO. So YOLO performs poorly in small objects. Mm, So that YOLO divides the image into a grid. Small objects occupy a tiny portion of that grid cell. Because of that, other objects may cover that or overshadow that. So therefore, it works bad with the small objects also. So these kind of problems are there. So this does not happen in other networks, two-stage detectors. Mm. Location accuracy suffers compared to faster RCN due to causal feature errors in small boxes. So location accuracy is also a problem because now it's you can see the output structure is from a 7 by 7 grid. I think that's a problem. I didn't think about it now to be definitively explain that. But anyways, because of this 7 times speed up over fast RCNN, so it ran up to 155 frames a second. That was very fast. Performance on Pascal VOC, if you take the fast RCNN, um, correct 71%, YOLO correct 65%, location errors, I think. Fast RC in 86%, this one is 19%. Yeah. Background errors, fast RC is making background errors, right? Yeah, background noise is less. Okay. Yes. That was YOLO version 1. And then YOLO version 2 was also by the same authors, Joseph Redmond and others. Mm, mm. They are the main thing that they produce was the so-called anchor boxes. These anchor boxes, uh, now the bounding boxes, two bounding boxes they had some, I think, initial sizes maybe, or they had to start from some number and go. Um, Let me see whether I can find that in the paper. Maybe I don't remember this. How they initialize the bounding boxes. I cannot find it. I don't know. Um, or they initialized. So, anyways, this network had the so-called anchor boxes. Um, and then they had batch normalization and other tricks. Um, so you can see YOLO V2, the performance frames a second and so on is much better than YOLO, especially in regarding the accuracy, much larger accuracy. This YOLO's responsibility, up to YOLO V3 also, the original authors did that, I think. And then after that, a lot of authors came up with YOLO papers, I think. Then these people have the YOLO versions 5, 8, and 11, and so on. So we can use their network to do that. It's an extremely good object detector. Mm, very fast. I do not know how the new advancements have happened after these versions. So you have to read individual things by yourself. But I think the basic understanding that we got is sufficient for you to think about these things a little further. Mm. Mm. Ultralytics is the one that people use now. So I have a little piece of code to quickly test this from the sample code available on that. So this is from the um, Torch website. YOLO V5 is there. So I did not do much. So, but you can see the parameters, number of parameters, YOLO V5, 6, 7, and 8. You can see the COCO in maybe 50% to 95%. Now I hope you understand what these numbers means. It corresponds to the IOU and on the validation set. Mm. So you have to install pip install minus u ultralytics and then use this one. So Torch upload this one, YOLO 5, pre-trained one, pre-trained true, and you load an image and then you get the result, model image results, and you can print or save the result. This is very simple. So this is exactly what I did. So this is their Zidane's image. So this is already downloaded. So training parameters are downloaded. So nothing much to, it's not required to train, but you can test it directly. So you can see it has detected 0%, X min, X, Y min, X max, Y max, and the confidence and the class. Class is the person, right? So one, two, three, four, showing the location. Of course, it does not show the scent and the width and height, but now it has computed the bounding box top left and bottom right corners. You can do that. And then one is also a person. And then two is a object class 27 Thai. Three is this one. So I have that image saved somewhere. I think it is saved runs or something. Runs. This is the one. So you can see just detected these two persons and these there. And looks like a cell phone to it at the time. Yeah, this is wrong, right? So cell phone confidence is 0.27. So you can see it's very low confidence, right? It is 0.27 for the mouth, it's calling a cell phone. So very easy to get this running. Um, but then I did this one from Alterytics. I imported. I went to the Alterytics website and how to run that. So I don't know where I got that. So I think this one is what I wrote. And yeah, yeah, this is the code. So simple YOLO V5 training and inference example. So it trains also for full documentation, see the modes and see your product trainers pages. So so this passes the configurations to that, and then you can get the information about the model and train it for 100 epochs, 600 images. So I ran that. We can run that. It doesn't take time too much. So, oh, okay, this is wrong. I made a mistake there. So I ran it on one of my images. Let's run that again. So its structure is being shown that the now the convolutions it has and the different parameters it has and so on. I don't know too much about this version of YOLO 11, so you have to go through it to understand what these things mean. I actually do not know. So now the training is starting. So I have a GPU in my laptop. That's why its GPU memory is being shown like it has a 2 GB GPU. So epochs are running and they are quite okay. So it's quite fast as you can see. So mean average precision at 50%. IOU you can see it's quite high. Box loss, glass loss. Anyway, we can let that run and we can come back and see. Um, so we will look at few more of them. This multi-resolution prediction in the SSD paper, single shot multi-box detector, they are predict the boxes of different sizes from convolution maps. Each level of resolution has its own predictor. So different resolutions have been used. So therefore, you can see it definitely uh, uh, helps the uh, different scales much better than the Euro-like versions. Mm. Also, you can see this kind of these concepts coming into later versions of YOLO also. So we will not go through these things. One thing that you can see here is feature layer, feature layers from the previous layers, see, are being fed forward. So can you see that it's the features layers from different scales are being used to do the detection in the SSD. Then we had this new concept called feature pyramid networks in 2017. There you can see the feature pyramid network. So you have the original image here. Of course, when you convolve, the size changes. And then they took this, do the prediction and added them another layer, do the prediction and so on. These kind of things they did. So of course, when you go from this to that, you have to do 2 times of sampling and so on. So this improved the predictive power of the lower level features maps by adding extra contextual information from higher level feature maps, predict different sizes of the bounding box from different levels of the pyramid, but share parameter predictors. So these are this is a contribution made by this feature pyramid network. So popularly known as FPNs. FPNs. And then this was actually a student paper. It's a very famous paper now, focal loss paper. It's called RetinaNet. Their classification subnets predicts the probability of each object at each position for each of A anchors and K object classes. Box subnet, each position and each anchor predicts offsets to ground truth box. Class subnet and the box subnet. This also uses the anchor boxes and also it uses the feature pyramid network. And it uses this so-called focal loss. That's the main contribution to the paper, as I remember. Downweigh the standard cross-temporal loss so for well-classified examples. So you can see this is the so-called cross-entropy loss, and now if this probability is, let's say, zero 0.9, if it is 0.9, if it is 0.9, uh, this PR point, if it is 0.9, then this number will be 0.1, right? Number will be 0.1. So you can see that 0.1, you raise it to power, let's say for easiness, we'll put gamma equals 1. So well classified ones, you down way. Ones that are not properly classified, you up way. Can you see that? So this is the contribution of this focal loss. I hope I probably explained that. I did not study that recently. This long time ago I studied this. So that's important. The retina aneuploidy, so you can see the retina anet 101 is with the ResNet 101, I think, and so on. So there is us Foco average vision, inference time, and so on. They have given YOLO V with the YOLO V2, SSD, and so on. So this one I have not studied this, so I unfortunately I will not be able to describe that. But I want to show you the last one. This is that with the transformers, the detection transformer. Deter this paper. This is an important paper that can be used by you also. These are end-to-end object detection with the transformers. So we did not study about the transformers. So next time, hopefully, we will study about the transformers. So I'm sure that you can use that object detection in the transformers also. So that's known to be a good object detector. Well, in Hugging Face also. So that's all I want to talk about object detection. Make a mistake, I think some mistake may have happened. So it has identified 5 persons. Uh, so printing didn't work. So let's see whether we can save it. I think some mistake. Yeah, some mistake there, but you can see it has detected 6 people. So this image that I put is this one. Maybe there's a mistake, right? Not 6 people. Only 3 people are there or something. One, two, three. It has detected 6 people. I don't know where. I could not save it also. So there you can see uh, training also taking place here. So for this is summary. So accuracy is there. MEP 50 is extremely high, you can see. So it's very easy to get them running. That's what I want to show you. That I do not know about this and I don't use this very much, but they are very easy to get them used. Okay. That's all I want to talk about object detection. Give me a second to until I briefly start the This is the segmentation uh, lecture. I just uploaded slides, so if you want to download them, please download and write something down if you require. But of course, the video is being recorded. So we'll briefly understand this and look at few of the classic techniques. Yeah, so introduction, there's a way called thresholding, region growing, k-means clustering. Uh, all of them I will not do. I will do a few of them. So segmentation means simplifying an image to a meaningful pixel groupings. These are extremely important because especially in medical image work, segmentation is a major part. So I will show you one work that we have done perhaps. I have shown this before. This is our work. Actually, um, you can see here we have three ultrasound scans obtained at here, and there. So these are very noisy scans using bad probes, and we have a segmentation network here. You can see the segmentations of the liver, and then we do some processing, and we are able to obtain the 3D reconstruction of this. So apparently, this has been demonstrated on 19th at this Disrupt Asia. Uh, all right, so you can see that in that example also we partition the image into two, foreground versus background. So that's segmentation. Partitioning an image into parts for deriving meaning for further analysis based on some homogeneous characteristic. So process of assigning a label to every pixel in an image such that pixels with the same label share certain visual characteristics. So you can see here, it's not classification, it's not object detection, it's actually assigning a label to every single pixel. So semantic segmentation is one of them. So here is this segmentation output. We call it semantic segmentation because we are giving labels that are meaningful to human beings. So for this area, we call wall. So you can see the lines have been drawn and the chair area has been identified and so on, right? That's labeled image. So binary segmentation means you use the, for the llama area, foreground label, white, for example. For the background area, use background black, for example. So this is segmentation. This is a binary segmentation. Okay, so see, here you can see some segmentation outputs on known data sets. So it is breaking the image into coherent objects. And you can see these are the human segmentations. Humans know how to exactly draw the lines in images. So if you take an artist, that artist may also draw something like that, the segmentation boundaries. So sometimes supervised, unsupervised. So this is an image from the so-called GrabCuts paper. It is available in OpenCV also. There you just have to draw a rectangle like that around the object that you want segmented, and it will segment that out. Or you can draw using different colors of pens. That means the background pen and the foreground pen. It will segment the foreground. So these are important if you want to take a part of the image out and paste it in somewhere. In the new phones also, you have this, you can keep long press the object and it will allow you to segment that. Extracting blobs is the sort of segmentation, but for example, triangle blob, the this gravel blob, the grass and the river. But this is very hard. Uh, what are blobs? They are regions of an image that somehow are coherent. Why blob extraction, object removal, composition, and others are very important. Um, but are these blobs objects? That's also a question. In general, they are not. So simplest way to define object coherence is similarity or brightness of the color. Based on the color, we do that. So for example, if you take this tools image, you can see these are black and this gray. This area is gray, right? So based on the color, we can segment. Here, this is brown and grass is green and sky area is blue. And based on that, you can segment. So So we will look at some of these things. Uh, if you take this tools image, uh, you can see we can just, if you look at the histogram here, you can see corresponding to the black areas, you will have some pixels. Okay, you can see this is from 0 to 255. This is called histogram. So we just count how many pixels are there with this intensity, how many pixels are there with this intensity, and so on. So most of them are close to white or gray. That's why you have a high peak here. So you can see if we take the pixels that are lower than some number, and you will get the tool area, right? So you can see the mask is if one is if mxy is greater than t, mask xy is 0 if mxy is greater than t. This is so easy to segment. So T is the threshold, user defined or automatic, same as histogram partition. So this is the thresholding operation. It's a very simple way of segmenting, but it's extremely fast. So these are good for sometimes for things like thresholding. It's good for fingerprint segmentation. You can see the areas that these lines are there have been nicely segmented because it's a two model, bimodal histogram, the black area and the white area. So what are the potential problems? So many segments, right? And the noise is also coming up. That's a proper problem with this. Okay. So thresholding usually, although we think is easy, it is not always successful. For example, if you have shading here, you can see there's a gradient or something like shading. Then if you apply a threshold, then parts of the uh, background, this is also background, right? Comes as an object. Pass, yeah, that is the problem. So then you can say, okay, let's divide it into small rectangles and apply thresholds. But for some rectangles, parts of the background has become the object. So this is a problem. So therefore, we have a method called region growing. I will do this and finish region growing. That's very easy to understand. What we want to do is start with a seed. Now here is a seed. Here is a seed. And start with the initial set of pixels called seeds. Add to pixel at pixel P in K, their neighbors Q if the intensity difference is less than a threshold. So we consider the neighbors. We consider this neighbor, this neighbor, this neighbor, this neighbor. If you consider four connected neighborhood. Let's say this intensity of this pixel is 100. This one, let's say, is 90. And let's call this threshold T equals 25. So you can see that 90 minus 100 is 10, it's less than 25. So you add that also into the region. So this is what it is. So if you take this pixel as 80, that also gets added. This pixel has 94, that gets added. This pixel has 78, that gets added. Can you see that? So, and they will get added, but at the edge, at the border, then you will have a problem because not a problem. You have the intensity is much less than that. Maybe this pixel will be 50 intensity. Now that does not pass the threshold, so it does not get added. Okay. So this is the region growing. Okay, I will show you the animation now. You can see, consider the neighbors and all these things get added, right? Get added, but when it reaches the boundary of the object, now they no longer pixels, neighbors do not pass the threshold, so they do not get added. So this is repeat until nothing changes. This is region segmentation by region growing. Is this the same as global thresholding? Absolutely no. Why? Because this will give you only one single coherent segmentation, not multiple. In the region growing, you had multiple segmentations. Right? This will be one contiguous region. So this is good for things like detecting these welding problems and so on. So the shape does not matter and so on. So, but region growing also has problems. It leaks at a weak spot. So for example, here maybe you have a weak spot because the object colors and the background colors are almost the same, then it can leak there and go into the background also. So there are ways to prevent that. We will discuss about them next week. So here you can see it, they have used region growing to segment the water, but you can see here there is like almost near similarity between the ocean and the sky. Because of that, it has leaked into the sky. Yeah. Yes. We'll do a brief problem and see. This image has three perceptual distinct regions, region A, B, and C. Where would image thresholding fail? Will it be able to segment out region A? No, right? Region A not possible because it has a shading. Region B, no, because it will have similar colors are there in region C also. B also cannot be segmented. Region C, not possible because it cannot be defined by a single color. So therefore, region C cannot also be. Region proving, I would feel usually it may work in region A. In others, it's not true. So either A and B are merged, or region C is split into many small regions. So A, B are merged. So uh, yeah, you can see the answer. Okay. So as time is running out, let's finish here. Next time I plan to carry on with the segmentation lecture, and there's one important part we need to cover. That's about the transformers. I will cover the transformers and talk about briefly about the new trends and finish. I think next time will be the last lecture. But I am not sure about the my participation in the next lecture because I have to attend the prize giving. So I will discuss with the people who are administering about whether I can skip next week and go for the week. Yes, thank you very much. If you have any questions, you are most welcome to ask. Otherwise, we are okay. You can log off. Now, there's a quiz. Please do the quiz also. Thank you very much for participation.
Yes, sir.
Thank you. Is there a question? No. Okay.